interesting. And we are a bit running late, so let's jump directly to the next talk. So Farzaneh is going to talk about end-to-end verified trusted execution environment. And as soon as we're okay, we're set up. So take it away.
Okay, thanks. I'm Farzaneh Derakhshan, and I'm going to talk about our work towards end-to-end verified TEs, in which we use verified interface conformance and interface preserving compilers. This is a joint work with Zichao, Zhang, Amit, Vasudevan, and Limin. So the goal of the trusted execution environments is to provide a secure world for applications that have some high privilege code or access, some confidential data. And we want to, so these trusted execution environments have some mutually distrusting applications in them and are run on a trusted operating system. And they're usually on like the same device as a non-secure world that using a normal operating system and have multiple untrusted applications. So these secure and non-secure worlds share the hardware, they share the memory, input-output devices, page table, control registers, and they run on the same set of cores. There are multiple applications of these. For example, in cloud computing, you usually put your like secured applications in a device that has, a normal device that have like untrusted applications on it too. Secure banking, and there are some examples of trusted operating systems that you can see. Okay, so let's say that there is a bug in the trusted operating system, or an attacker can get access to it. And because it's a high privileged world, they can easily access the like the shared memory. They can easily access input-output devices, maybe control registers, and via that they can also access the non-secure world. So basically, any subversion of a TE means full control of the attacker over the entire platform. And the goal is to make sure that the metadata, including the page table and control registers, are protected correctly. For example, we want to make sure that the flag of the page table, the last bit of the flag is always put to 1. And there are two different approaches on that. You can put there are some hardware solutions that design some hardware architecture, or there are some software solutions, and we are one of them. We want to give a software solution for these TE environments. Well, if you have a formally verified TE, then we have removed many of these vulnerabilities. So one approach is to prove that our TEs are fully functional correct, which it has been done, for example, in Ironclad, Cell 4, or Certic OS. And it's a very strong guarantee, so it's good. But there is a disadvantage to it, because you have to prove the full functional correctness of the whole system. Then it means that it's not so developer friendly or update friendly, and there is a high cost of verification in terms of cost of like time and money. And it's kind of an overkill if you want to ensure only some specific security properties. So what we are after is to verify specific security properties of these TEs instead of a full functional correctness. And there has been prior work using this approach, for example, XMHF, Uber XMHF. And the advantages would be, because you're only after this specific security property, it would be more development friendly, and you can use source level automated verification tools. But the biggest disadvantage is that there will be lack of guarantees on the compiled code, and this is what our work is going to address. We want to bring down these guarantees down to the target level. So our goal is to have some lightweight verification for TEs. And we are going to verify just specific security properties, for example, that I told you, like that specific properties about the registers or page tables. And we want to use off-the-shelf verifiers and compilers, and we want to bring these properties down to the binary level. So the technical approach that we are going to take is to advocate for a programming paradigm that uses compartments. So we want the programmer to write their programs in compartments, and these compartments have exclusive resources and some verified interface. This is an idea that we took from the prior work, UberXMHF. And in the prior work, they called this small compartments Uber objects. So I'm going to call them Uber objects too. And we want to use this compartments as units for sequential verification and compilation. And our theory would be that if we verify these compartments sequentially and in isolation, and then compile them sequentially and in isolation, then we can compose them in a concurrent setting, and we get the same properties that we are after in the concurrent setting too. Okay, so this is the TE picture that I showed you earlier. We are interested only on the secure world and the hardware that it's interacting with. So we want to prove that this secure world has these properties that we have, that we want. And we advocate for programming the applications and the OS in the secure world as compartments. I just interchangeably call them Uber objects. Okay, so a compartment it's like a regular object. It has some internal functions that implements it, and it also has a public interface with which it can communicate with other compartments, with other objects. But the difference is that it has, this shared memory. It has some exclusive resources here on the shared memory that only this object can have access to. So it's exclusively for this Uber object. No one else can touch it. Right. And the public interface have some pre and post condition, and the properties that we want to verify are basically these post conditions. So we want to verify that when the public interface is done, when it returns, this post condition always holds, assuming that when it's called, the precondition is satisfied. And the same with with all functions in the public interface. Okay, so we want to let's say that we have two Uber objects, and they have we want to verify this invariant phi, which you can think of it as our post condition, the security property that we want to verify, and we want to ensure that they have this memory separation. What we do is we verify them individually. We verify each of them. So we use compartments somehow as units of verification. And then when they are verified, now we compile these verified compartments down to the target level. So again, we compile them each. So we get now our target level compartments that are written in target language, for example, assembly. And then we show that if we run them concurrently, a translation of the invariant that we were after also holds in any concurrent execution. So that is the main model that we have. And it has some benefits. Well, we can use lightweight verification because we'll have lightweight verification because, first of all, we can use off-the-shelf verification tools. Each compartment can be written in a different language. They're not necessarily in the same language, and they're extensible. So you can add a compartment, or you can update one compartment individually. Well, the challenge to get this benefit is that we need to be able to compose these sequentially verified compartments together and to get source level guarantees. And then we want to support concurrency and interrupts. So of course, the challenge is to handle concurrency and interrupts. And for that, we need a high level abstract semantics. And the last benefit is that we have target level guarantees. For that, we need to preserve the sequentially verified guarantees down to the target level. And we want to use off-the-shelf compilers. So we have to prove that our there is a good compiler, there is a good off-the-shelf compiler, and we in particular prove that CASCompCert, which is a form of compositional COMCert, has this property. Okay, so in the rest of this talk, I'm going to give you an example of concurrent execution to show you how our abstract semantics work. I will talk about what are these source level guarantees, and then I will talk about the target level guarantees, and I show you how we can use off-the-shelf tools, and then briefly I'll talk about the related work. So let's say that we have two Uber objects, Uber object F1 and F2, and each of them have their exclusive memory. It's important that we want to ensure that this Uber object 1 cannot read or write from the exclusive memory of Uber object 2 and vice versa. And we have two cores. So, and these cores are independent from the Uber object. So they share these two cores together. So let's say that we load the public interface F1 of Uber object 1 on core 1 and public interface G2 of Uber object 2 on core 2. And now these cores have access to these exclusive memories. And we run them concurrently. But at the middle of the run, Uber object 1 wants to call an function, an interface of Uber object 2. This wouldn't be possible because this G2 is already loaded on core 2. So it has to wait until core 2 is done and somehow release this exclusive memory. And now we can load the public interface of Uber object 2 on core 1. And now it gets the access to Uber object 2's exclusive memory. Again, we run it internally until it's done. And then it goes back to Uber object 1 and continues the rest of the work after the return. So this is an example of how we run these Uber objects concurrently. And our abstract, we have an abstract semantics that model this. Okay, so now we want to show what is the sequential guarantee that each Uber object has to verify, or we have to verify each Uber object to make sure that they can be composed together. So let's say that we want to verify Uber object 1. Well, if there is an internal step in Uber object 1, then what we need to do is to make sure that for any internal step, if it touches some part of the memory, so this sigma is the whole memory, this part is the memory that does not belong to Uber object 1, and this part is the exclusive memory of Uber object 1. If we take a step, the memory will change, but we need to make sure that the footprint of Uber object 1 is exclusively inside it's inside its exclusive memory, right? So we have to assert, whenever we verify this Uber object 1, we have to assert that the footprint is entirely restricted to the Uber object's exclusive memory. And when there is a concurrent step, for example, on Uber object 2 wants to concurrently step on another core, well, we don't know what is the code of Uber object 2 when we are verifying Uber object 1, so we have to rely on Uber object 2 being good and not touching our memory. So whatever the footprint of other Uber objects are, we rely that they are on the rest of the memory. So it's kind of a rely guarantee reasoning about accessing each Uber object's exclusive memory. And we have the same rely guarantee for pre and post conditions. So you assert your post condition, and but you assume your call is post condition upon return. Okay. So what we prove is that if if you verify each Uber object that they are interface respecting the relay guarantee property that I showed you in the previous slide, then in any concurrent run, the caller would satisfy the preconditions of the callee, and the callee satisfies the post condition upon return. And we proved this theorem by proving progress and preservation for our abstract semantics. And we also proved that our concurrent execution is data race free, which is kind of straightforward because we have these exclusive memory accesses. Okay, so now what about the bringing down this to target level? We want to specify some properties about our compiler that ensures that we can bring down the properties from the source level to the target level. Well, a compiler consists of two parts, a memory transformation and a code transformation function. The memory transformation, so here is a source level object, a target level object that is compiled with a compiler. The memory transformation transforms this exclusive memory at the source to the exclusive memory at the target. And we want to make sure that this memory transformation is well defined, meaning that basically it means that it doesn't screw like heap and stack, pointers and heap and stack in the memory. So it has to be a total and injective function from heap to heap. So the compiler cannot compile a heap location to a stack location. And it has to be consistent among all compilers that we use for each Uber object. And then there is this code transformation function that translates the code. And we want that specifically to be interface preserving, meaning that if an Uber object respects the interface at the source level, then the Uber object has to also respect the interface at the target level. So that is the main property that we want from our compiler. And then what we prove is that if we verify each source level Uber object to have to be interface respecting, and we compile each verified Uber object with an interface preserving compiler, then at the target level, we have this good property that the caller satisfies the preconditions of the callee, and the callee satisfies its post condition. And in particular, we prove that CASCompCert, that compositional form of CompCert, is interface preserving. So it's a good compiler that we can use. So now we can put this together. So let's say that our source level compartments are written in C. We can verify them using from a C, and then we can compile them using CASCompCert, and we get target level compartments that will have the property that we verified sequentially for each Uber object. So one bit that I didn't talk about in the presentation is that we allow our Uber object to have some kind of assembly code inside them too. And to be able to verify them, we write them in some domain-specific language called CASM. And so one of our assumptions is that this domain-specific language is sound and it reflects the assembly semantics accurately. The other assumption that we make is that the C verifiers logic is sound. So meaning that it only verifies correct predicates. And finally, we assume that because, for example, if I want to compose CASCompCert from a C, it's not necessarily the case that their C semantics is the same, their memory model is the same. So we assume that they agree on the C semantics and the memory model. Okay, so there are several related works. I will first talk about like the threat models. So the threat model that we use is very similar to the CompCert style compiler correctness, meaning that if you assume that at the source level you have some property, then you can bring it down to the compiler level. But there are more more strong threat models like fully abstract compilation and robust safety. And they talk about like, what about there is a low-level attack and adversarial environment in the in the target level, and we don't address these two. And there are several works on compartmentalization, both on the software compartmentalization and on hardware with Cherry. Okay, so to conclude, we have this compartmentalization for implementing TEs that enables us to achieve this compositional verification, that we can use certified compilers to bring them down to the target level. We also have 2 case studies showing that our security properties can be verified on 2 existing open source TEs, up to down to x86 and ARM platforms. And there are some points for discussion about like how we discharge assumptions and can we use a more powerful attacker. Yeah, that's it.
Okay, thanks for this very cool presentation. We have a few minutes for questions. I guess Katalin is the first.
Yeah, very nice. Working? Okay. So, well, my first question relates to what do you really prove about the C code? In a way, is it that you at least prove that it's memory safe and has no undefined behavior, like as a baseline before even being able to show any more interesting specification about it?
What was the like first part? What do you want?
So if any of your compartments has undefined behavior, then I guess all the guarantees of compilation would be
right. So we assume that there are no undefined behaviors.
And I guess you prevent that by the verification at the C level, right? With formalize.
Right. So if there are some undefined behaviors that we can, catch. For example, you cannot touch some other people's, stack or something like that. But if there is an undefined behavior that led to abort, then our proof doesn't work. It says that like, no, this is an abort, and so we basically need this. We assume that they have good behavior. Okay. Yeah.
And well, maybe follow up. So if this is the minimum thing you prove, you mentioned that you don't do full functional correctness, but at some point you do some notion of correctness. You have the specifications for each piece of your code.
Right.
Like why isn't it full functional correctness? Like what are you, I guess because you're looking at some more lightweight properties, but can you tell us what, say, for instance, what you proved in your examples, what kind of properties they were?
So it's not full functional correctness because we are not necessarily interested in like every security or every like we are not interested in every security property or every like behavior of the code. We are just interested, for example, like we want to make sure that in one of our case studies, we want to make sure that the page table is set in a way that no untrusted like application can access it. So as long as this thing is verified, we're good. We are not really interested in like it's fully correct or something like that.
Hi, I have 2 questions. So the first question is, this approach is suitable for any code, or can I just take like Linux kernel and apply that, or it's have to be substantially reworked to apply this approach? That's the first question.
Is it written in C or in?
Yeah, C.
Yeah, I think it should be okay to use it like for any code.
So I don't have to change the source code in any way
to
reshape it.
Well, I think to answer one of these assumptions, you need to make sure that the CASCompCert and, for example, your verifier agree on, the C semantics. So probably you need to bring it down to C minor something like
No,
that.
no, that's understood. But for example, when you're saying about Uber object, you say like, okay, this part of the code needs to access only to this part of the memory.
Right.
But this code needs to be written in a certain way.
Right. So it has to be written using these compartments. You have to follow this compartmentalization. You need to make sure that your internal functions are only calling internal functions or the interface of other Uber objects. And they cannot, for example, call their own interfaces. So this has, or you cannot call someone else's internal function. But yeah, as long as you're writing your code in objects, then I think it would be fine.
Okay. And the second simple question is that if there is any performance overhead.
I think well, so for example, you cannot access every part of the memory yourself. For example, if you want to, touch some part of the memory, you have to call the Uber object that touches that part of the memory for you. So I think that may cause some performance thing.
Like
Yeah.
example you showed with 2 ports and 2 Uber objects, you said have to wait to load other Uber object to the first port to access it. So
Right.
So it will be interesting to see a measurement, see how it's impact the performance. Thank you.
Right.
Maybe.
Yeah, I don't think I need one. So,
But I think we have.
all right. So this setting seems very similar to me to the setting of smart contracts on the blockchain. You have a bunch of communicating things that are kind of, they have the ability to access each other through public interfaces. And a big problem there has been reentrancy. So one Uber object calls into another, and while it's in the middle of processing it, the second one calls back to the first one.
Exactly. Yeah.
And I'm curious how that shows up in your framework, because the general problem is that some invariants that were being maintained by the implementation of the first contract might be kind of temporarily broken while it calls the second contract, right? So even though the second contract is sort of maintaining all of its spec, yeah. So anyway, is that an issue for you?
So I think maybe it's not an invariant. It's more like the post condition that upon return or upon like calling them, you have this pre and post condition. And also, I think because you have this exclusive memories and your post condition is about your own exclusive memory, maybe they don't interfere with each other. Does it make sense?
I don't think that's going to save you here.
Okay. So
the problem here is that I don't know how you frame, maybe it comes down to the power of your precondition and postcondition language and what it can actually say about possible side effects on other contracts.
Right. So we also have this, I think the memory separation would save us because you can never affect the post condition of any other Uber object because you never touch their memory.
The problem is that with a reentrant call, you're calling back into the original object while it's still in the middle of processing one of its calls.
Oh, so you cannot call them if they are running. You have to wait until they're done and then you can call them.
So they're running on the same core, but you still can't call them.
No, you can't.
I see.
Yeah.
Okay, so okay, fine.
Yeah.
That makes sense then.
Okay, let's thank the speaker again.